Oh, okay.
Thank you so much for coming. So this is Will Yang's Ph.D. dissertation defense. I'm the chair of the committee together with Dan Konicek, Aaron Johnson is on Zoom, and Michael Posa is the advisor. So we're gonna listen to Will first, and we'll have a round of questions from the committee, and we can have some questions from the audience. Then we're gonna kick everyone out, we'll discuss, and then we'll have the decision. Right? So yeah. Take it away.
Thanks, Nadia. Yeah, thank you to everyone who can make it here this morning, as well as those joining on Zoom. Today, I'm really excited to be able to share my work on controlling context transitions for dynamic robots. Our vision for robotics is to be able to deploy general purpose robots in diverse environments and have them perform a wide variety of tasks. This vision has led to the recent development of humanoid robots that are designed to mimic the human form in order to navigate and interact in our human-centered environments. We have been making a lot of progress towards these general purpose robots. It seems like there's a new demo video being released every month, but we're still far away from achieving that vision. So let's look at what a possible pipeline to achieving capable and taskable general purpose robots could look like. This is a very sparse simplification, but the workflow could start with first parsing the command, which could be something like clean the backyard or wash the dishes. There's been a lot of interesting work on grounding language into physical affordances. Next, we can turn that command into a sequence of actions, or what I will call low-level capabilities, using methods from the task and motion planning literature. And finally, we would execute those low-level capabilities on the robot. We've seen impressive improvements in terms of parsing language into actionable tasks, especially recently in the context of LLMs. However, when we look at the low-level capabilities of when the robot actually has to physically interact with the world, it's clear that there's still some clear limitations. When we compare the types of capabilities shown in these demos to what humans can achieve, there's a gap in terms of the dynamic capabilities. In contrast to this robot walking carefully across the perfectly flat ground in the lab, humans are capable of traversing complex and challenging terrain using incredibly dynamic maneuvers such as running and jumping, shown in this parkour video. Looking at manipulation, the robot is slowly and cautiously making contact with each of its fingers in order to establish a firm grasp of just a single object. In contrast, humans are capable of confidently handling multiple objects at a time, such as loading the stack of plates into a dishwasher. While these examples may seem flashy, they showcase some of the key benefits of operating across the full range of dynamic capabilities. For example, it allows us to access new agile behaviors that enable robots to reach new areas that would otherwise be inaccessible. For example, jumping is required to traverse these rooftops. Second, we can obtain significant efficiency gains by exploring the underlying dynamics of the interactions, such as allowing plates to slide into place. Although we may not require these robots to do these crazy stunts, pushing the boundaries of what our robots can do can still lead to useful improvements in more practical applications. However, there are many challenges that we encounter if we want to achieve these behaviors. And today I'm going to focus on what I think are the most critical, which are impact events and frictional contact. By impact events, I mean when the robot comes into contact at speed with the environment. And by frictional contact, I mean leveraging and reasoning about the sliding contact mode. And just to clarify, I do want to recognize that there are existing methods for planning for motions with friction, impacts and friction. Right now, we can synthesize incredibly dynamic and contact-rich motions, but realizing them via real-time control is still an ongoing challenge. Additionally, there's a ton of theory for real-time control within a single contact mode, and it really only falls apart when we want to do real-time control across contact modes. And that's a key challenge thus lies in how we control the contact transitions, such as the transition between no contact and contact, and between sticking and sliding contact. The goal of my work is by developing methods that can robustly handle contact transitions, we can expand the low-level capabilities of our robots. Today, I'll first go over some preliminaries about how we think about control, specifically the control hierarchy. Next, I'll talk about my work on control during impacts, which introduces this framework called impact invariant control that enables robustness to uncertainty in the impact event. I'll show how it's critical to enabling dynamic maneuvers such as jumping and running. Then I'll move on to a dynamic manipulation task that heavily leverages sliding contact. In that work, I'll show state-of-the-art capabilities in controlling between sticking and sliding contact, and discuss how we can leverage contact implicit MPC to produce a general method that can replan in real time to handle the known inaccuracies of frictional contact. I want you to know that although I'm using locomotion as an example for impacts in manipulation, for example, of frictional contacts, the principles that I'll discuss in each can be broadly applied to either application. Okay, so first off, we're going to talk about some preliminaries to understand how we think about control for these robots. To avoid any confusion with the previous control hierarchy from earlier, this framework is purely to realize the low-level capabilities. And from here on out, all the methods I'll discuss will remain in this context of enabling these low-level capabilities. As most general, controlling robots involves a feedback loop where we take in some sensor measurements about the state of the system and apply control inputs, typically as motor commands, in response to those measurements. In the work discussed today, we use a control hierarchy to separate the controller into a high-level planner that sends general reference trajectories that are then tracked by a low-level controller. While there are generally no restrictions on the update rate of the high-level planner, the low-level controller typically needs to run at a kilohertz or faster in order to stabilize the system. So first off, we're going to talk about high-level planning. The question is, how do we generate these reference trajectories? And right now, for simplicity, I'm just going to discuss one method, which is trajectory optimization. The goal of trajectory optimization is to find a trajectory that minimizes some cost objective subject to the dynamics of the robot. We can impose additional costs and constraints to further define the motion. For example, for this long jumping motion, we can specify that the feet must land X meters forward. However, the optimization problem we are trying to solve to achieve this can be highly nonlinear, which means that we don't have any convergence guarantees, and often it takes a long time to solve, typically on the order of seconds to a minute. And this is the reason why we need a high-frequency tracking controller to stabilize the plans. In this work, we use something called operational space control, which can track references. They can be kinematic functions of the robot state, such as the position of the feet or the position of the pelvis. And we refer to these as task space, or as indicated by the name, operational space. Given a task space reference, we can use forward kinematics to get the current task space state of the robot, and through feedback, we can stabilize the robot around these task space references. We do this by solving a small optimization problem every control iteration. Okay, now with the preliminaries out of the way, we're going to talk about my first work, which is on control during impacts. To understand why impacts are so challenging, we first need to understand rigid body dynamics and impacts. In our work, we model our robots as a collection of rigid bodies, and we can define the state of the robot using the positions and velocities of the robot. This includes states like the position of the base link, as well as the joint angles. We can express the dynamics using the following equation, and we have the quantities defined below. Importantly, the contact Jacobian, which is J, maps the contact forces expressed in the world frame to generalized forces. This equation describes the dynamics for a given contact configuration, in this case, when the blue light is in contact, up until the contact mode changes. At impact, so when the red light touches the ground, foot that was traveling towards the ground is brought quickly to a halt due to large impact forces. To avoid modeling the complex deformations that actually occur during impact, we use a simplified assumption of rigid impacts. And under this assumption, impacts resolve instantaneously. So the continuous forces shown crossed out in yellow are assumed to be negligible, leaving only behind the contact force that we now model as an impulse that maps the pre-impact velocity v minus directly to the post-impact velocity v plus. And this, after the contact in the impact event is resolved, we can continue on with the dynamics now in the new contact mode. Okay, using structural optimization from earlier, we can, along with some additional constraints, we can generate a walk trajectory that satisfies these dynamics. For visualization purposes, I plotted the velocities for a portion of the trajectory to point out a few parts. What we have are two contact modes corresponding to left stance and right stance. They're connected by this continuity from the rigid impact map. Okay, the challenge of impacts lies in this extreme sensitivity to the uncertainty in the impact events. And examples of the relevant forms of uncertainty include things like geometry, which typically which typically for legged robots is uncertainty in the ground height. The sensitivity comes from the fact that the primary method of stabilization is through footsteps, and therefore slight changes in the ground height can significantly alter the dynamics. The next is timing. Because of the discontinuity from impacts, there can be a big difference in the desired trajectory before and after contact. So getting the impact timing wrong can result in tracking the wrong contact mode or reference. On the topic of related work on dealing with this uncertainty, there's a lot of interesting work that addresses sensitivity to geometry by finding trajectories that are inherently robust to uncertainty in ground height. These works all have slight differences in their formulation, but interestingly have converged to the swing leg retraction policy first discovered by Seyfarth and Geyer, which is to continuously change the angle of attack of the swing foot. These robust trajectories have been shown to be effective and actually will be using the swing leg retraction policy later on in our running controller, but it only addresses a portion of the challenges associated with impacts. On the timing side, because we want to track these discontinuous trajectories, detecting which contact mode we are in is really important, and there's methods for emphasizing both speed and accuracy. Along the same topic, even if we were to detect that contact was made earlier than expected, you still have to make sure that the control is well defined in that situation, which is this idea of reference spreading control proposed by Saccone and continued in follow-up works. Another thing that we have to think about slightly is also related is how uncertainty actually gets propagated through this impact event due to the fact that timing changes as well. And this is interesting work from Cohn talking about the saltation matrix and how that's the correct linearization through a hybrid mode. While this timing seems like all we would need, they don't fully address the issue with timing. And in fact, if we look at a figure from one of these papers, specifically this one by Yunin, we can still see controller spikes as a result from this uncertainty. And these controller spikes can destabilize the system. Putting the related work in context of the control hierarchy, the robust trajectories take the role of high-level planners. And the fast contact detection methods, as well as handling mismatches in impact timing, are part of the low-level tracking controllers. Although there's still interesting work to be done on applying these robust trajectory methods to more complex systems, I think the methods for establishing robust low-level controllers is still incomplete, as evidenced by the controller spikes. And to understand why it's not enough, I'm going to refer to this illustration of trying to track a reference trajectory during impacts. Okay, so what this illustration shows is this pre-impact trajectory V desired, and then followed by this rigid impact map that maps it to the post-impact trajectory V desired plus. Imagine where the true state is some velocity that's evolving on the pre-impact trajectory. We're actually tracking it really well. We're right on the trajectory. But due to some uncertainty in the ground heights, we made impact early, and now we're suddenly mapped to the post-impact. Well, because we're tracking to the pre-impact trajectory, now this is our feedback error. And this is really large. And this is what causes the controller spikes Now, the prior work has extended these reference trajectories so that first they're well-defined. And then we want to do really fast contact detection to detect that we actually made impact early, so we should be tracking to the spread trajectory, and then everything should be perfect. The reason why this isn't fully complete is because in reality, impacts don't resolve instantaneously. In reality, impacts are a lot messier than this. It's really, even ignoring just the physical springs on chassis, there's mechanical compliance in the linkages and also mechanical compliance at the feet. And all of this results in the reality that impacts cause a rapid but not instantaneous change in the velocities. To illustrate this, I plotted the joint velocities from 8 jumping experiments on the actual robot. And this plot is very heavily zoomed in. This is only 60 milliseconds of data, but shows that impacts take on the order of 30 to 50 milliseconds to resolve, which again, for our kilohertz rate controllers, this is 30 to 50 controller actions, which can definitely destabilize the system. Going back to our illustration, impacts actually look something closer to this, where there's a non-zero period of time, where there's a lot of uncertainty in the actual velocity measurements. All we can know that the velocity is probably somewhere in this gray region, and even if we were to actually measure this, which reference trajectory we should be using to track to, as well as is unclear, as well as because either trajectory would still result in substantial error. So if you're somewhere in between, the actual reference is not well defined here, and both will result in don't seem quite correct. So basically, trying to accurately apply feedback during impacts seems kind of hopeless. And when implementing controllers on real robots just have to do something special near impacts in regards to feedback. This typically takes on the form of some heuristics, such as reducing blending controller gains, or explicitly including a separate mode right near impacts, where robots essentially have to give up on tracking velocities at impact. This seems kind of drastic, and it begs the question of, can we do better? And can we make controllers robust to impact without giving up all feedback? Fortunately, the answer is yes. And to quickly explain why, let's look at a quick example. In their walking controller, Ghosn chose to use angular momentum at the contact point to help plan footsteps. One of the reasons why it was chosen is because angular momentum about the contact point does not change over the impact event, or is invariant to the impact event. The reason why is because impact forces enter at the feet and thus do not apply moments. Angular momentum about the contact point has some limitations though. It's only two-dimensional, which doesn't capture the full state of the robot. It requires assumptions about point feet and no vertical center mass velocity. But this property of being invariant to the impact event is really interesting. And what we want to do is generalize it. If none of this stuff about angular momentum made sense, just know that due to the structure of impacts, of how they enter the dynamics, there exists an entire subspace that's invariant to the impact event. If you look at the impact dynamics again, you can see that the change in velocities comes from this contact impulse lambda. If we look at the shapes of these quantities, for the planar biped, it has 7 degrees of freedom, but the contact impulse is only dimension 2. And thus the impact invariant space is dimension 5. For Cassie, the impact invariant space is even larger. If we include the compliant joints, Cassie has 22 degrees of freedom, and the contact impulse for a single foot is just dimension 5. Number 5, for those curious, comes from a single redundant constraint when considering 2-point contacts for the foot. Even when we factor in that these are underactuated systems, so they have fewer control inputs than degrees of freedom, impact invariant space is still significant. Okay, how do we find the subspace? We look at the rigid impact map and notice that if we take the left null space of M inverse J transpose, we can multiply that by both sides of the equation and see that in the impact invariant space, the post-impact velocities are equal to the pre-impact velocities. To illustrate this effect, we can plot the joint velocities from the planar biped from earlier and see that the discontinuity that existed previously, when projected to the impact invariant space, no longer exists. And thus, we no longer have the issue of needing to know which side of the impact we are on. And I also want to highlight that the projected velocities are not 0. These are still interesting signals that we can apply feedback to. Okay, this is using a reference trajectory from a simulated system, but what about real data, right? When it's like not so ideal. Again, we take the same jumping trajectories from earlier, and when we project the velocity to the impact invariant space, the previous very chaotic or very messy joint velocities at impact are now a lot more consistent and thus a lot more amenable to feedback control. To be explicit on how we use this for feedback control, we can compute Q using the closed form expression for orthonormal basis for the left null space of M inverse J transpose. If we have a typical PD controller, I'm going to ignore the feed forward term for just conciseness. We apply feedback on the projected velocities instead. So we're going to do this instead. And what this does is this ignores the uncertainty in the impact directions while retaining control authority over the unaffected directions. One final note about implementing the impact invariant controller, because we're still sacrificing some control authority, we don't always want the projection to be active. Instead, we only activate the projection near impact events. And we know when impact events are about to happen because of our reference trajectories. So in practice, what we do is we use a smooth function shown here, where 1 is active and 0 is inactive. And we use a smooth function because the whole point of this modification is to avoid adding additional discontinuities to the controller. Okay, now with the controller defined, let's apply this to a walking controller and for the planar biped, and we compare against two methods, one which is the default controller where nothing special is done at impacts, and the no derivative feedback controller where we just turn off all derivative feedback at impacts. I plotted the tracking error right around the impact event, with the left plot showing the error in the leg that's impacting the ground, and the right plot showing the error in the non-impacting leg. The gray region shows when the modifications are active. And if we look at the tracking error right after the impact event, which is here and here, you can see that for the impacting leg, the default controller overreacts to the impact event, which leads to significantly more tracking error after impact. For the non-impacting leg, the no derivative feedback controller is overly conservative and thus does worse for the tracking error on that leg. So our proposed controller, the impact invariant controller, does the best on both. I mentioned that the method we use for low-level control is operational space control, which doesn't only track joint angles, and we can specify the tracking objectives in a more general task space. We're still using PD feedback, just that the outputs are task space objectives Y instead of joint positions and velocities. Because of this, however, we can't use a projection matrix Q in the same way as earlier because these are in different spaces. And in fact, we can't just map the task space references back to joint positions and velocities because there's usually two low dimensional, and then that means that there's not a unique mapping that exists. Fortunately, there is a way to project task space objectives. Instead of individually projecting the references in actual state separately, we can project the error instead. This is fine to do because we are only concerned with the error anyway for feedback control. To project the projected task space velocity error, we solve this optimization problem. And while it may look complicated, an intuitive explanation for what it's doing is that we're solving for a missing contact force lambda that essentially cancels out any error that can be attributed to the impact event. For instance, if we made impact early, meaning that the measured state experienced contact forces when the reference trajectory has not, then it will essentially effectively cancel out the change in velocities in the measured state. And because we're not imposing any restrictions on lambda, it can handle the absence of anticipated impacts as well. Another interpretation, and the reason why it's a projection, is that lambda, after being multiplied by the task space Jacobian as well as M inverse J transpose, this is the vector that essentially brings the error down to the impact invariant subspace. Finally, we use the result to compute the projected velocity error. So before we're here, now this is the new projected velocity error. And just one note that this constraint, this weird looking constraint, is just a restriction that the projected velocity can't violate any constraints that we know to be active. For example, if a foot is on the ground before and after impact, that contact constraint would still be included, would still be active, and would be included as this constraint. And similarly, CASI has these four-bar linkage constraints, which are encoded as distance constraints, and those are always active, and thus would be included here as well. Okay, so I was going to say that this is our previous error, and this is the projected test velocity error. Okay, just a quick note, while this optimization problem may look complicated, it's actually just a constrained least squares problem, which means that we can write out the closed form solution, and this can be solved very quickly and fast enough for the kilohertz rates needed for our low-level controllers. Additionally, constrained least squares are projections, and in the paper, we show that this optimization problem is equivalent to the projection matrix Q if the tracking objectives are just the joint space targets. Okay, so after formulating impact invariant control for operational space control, we can use it for CASI jumping controllers. To make a jumping controller, what we do is compute an offline jumping trajectory using trajectory optimization. And we convert these to task space objectives so that we can intuitively modify the references in response to disturbances. For example, once we land, we want CASI to balance, and we do so by tracking the position of the pelvis relative to feet, which is easy to do in task space. We evaluate our method against a default controller without the projection. So left is without the projection, right is our method. And looking at just the impact event, which is where these controllers are different, you can see that the impact invariant controller results in much smoother impacts. Watch it one more time. The one on the left shakes and has a lot of vibrations at impact event due to overreacting due to uncertainty. We also apply this to a more dynamic box jumping controller. This method is actually identical to the earlier jumping controller. We just find a new reference trajectory, which we also generate through trajectory optimization. And we're also able to execute this on hardware as well, able to jump onto a box of about 40 centimeters. No, we didn't do a comparison with the other controllers on hardware just due to the risk of damaging chassis. There's a lot of failures up until this success, and each time we're very worried about breaking chassis. But we do a comparison through a parameter study in simulation. Here we look at a long jump and a down jump, and the perturbation is on the context switching time to be early or late. So this would be early, this would be late. And on the x-axis, we try different durations of when the projection is active, with all the way on the left indicating that no projection was used. What we see that is as the projection window gets longer, we're able to stabilize a greater percentage of the trajectories. Okay, now moving on to the running controller. We're interested in running because it presents some different challenges than jumping. In our jumping example, the robot only needs to stabilize a single jump. But when running, each step leads to the next, and thus tracking error can accumulate. And thus it's important to have as much control authority to reduce the tracking error as possible. Additionally, running only makes contact with a single foot at a time, and thus has a non-negligible flight phase, which results in it being highly underactuated, again increasing the importance of grid tracking. It's also interesting for impact invariant control because we're only making impact with a single foot at a time, and therefore the impact invariant space is larger. Okay, what do we need to consider when designing a running controller? First, we have to recognize that we can't just use the same approach as a jumping controller, which is to generate an offline trajectory. This is because we need high-level feedback to stabilize the bulk motion of the robot, which is not possible from offline generated trajectories. We could consider generating a gate library, but what we want to do is we want to command both the speed and the direction, which means that we'd have to create a library that can span the full space of these commands, which if we want to command both sideways and forward speed as well as direction, that's the three-dimensional space, which in generating a library that can cover that is infeasible. All this points to needing to replan online. And what we do is we can do this by generating easy to compute trajectories for the foot position, the pelvis position, and the pelvis orientation. And to carefully explain why we're able to replan online, what we're doing is we're previously optimizing over the full robot dynamics in order to obtain a trajectory. And now we're going to leverage known simple models in order to significantly simplify the computation in order to be able to replan in real time. Okay, what we do is for the foot trajectory, we use the well-known Rayburn heuristic, which chooses the next footstep depending according to the current velocity of the robot. And then to make sure we can construct a trajectory, we have to make a spline from the last foot position to the next foot position. And then we also want to take into account things like foot clearance, as well as we want to incorporate the swing leg retraction policy from earlier, which we do sort of with this heuristic way to choose the midpoint of the foot. And then from that, we can also add in continuity constraints to make sure the first and second derivatives are continuous. And this fully defines a spline. For the pelvis position, we use the slip-like tracking objective, which is this thing what we do is we use a constant height for the difference between the feet and the pelvis. And we try to use the OSC, the operational space control PD gains to make it behave like a spring-like system. And finally, for pelvis orientation, we want to maintain a neutral pitch and roll for the pelvis. And to specify turning, all we have to do is command a pelvis yaw velocity. So this defines all of our reference trajectories. And we feed this to operational space control. And the operator commands are sent here, which can command both forward and backward, as well as turning. And what this clock does is it specifies a nominal stepping frequency. We validate our controller outside of pen on the turf fields to show that we can run forward and turn. And I may have made it sound straightforward. I don't want to give that impression of that developing and running control is easy. There are a lot of challenges beyond just impact invariant control. It's really one of those motions that you have to like chase down every small detail and reconsider all the assumptions we're making in order to get it to work. So actually seeing Cassie run was incredibly rewarding. Okay, I want to emphasize that the primary contribution of impact invariant control is a really general method. Although we're using it for two different types of motions, which are jumping and running, the code for the tracking controller, which is where we make our modification, is actually the exact same. So all we need to do to compute the projection is the contact Jacobian as well as the anticipated impact time, and we're able to apply this to very general tracking objectives. To give context for the difficulty of achieving jumping and running on Cassie, the only other box jumping and running controllers demonstrated for Cassie were generated through reinforcement learning. Okay, in summary, the main takeaways are that the near discontinuous tracking objectives from impacts cause unavoidable uncertainty. And in practice, roboticists will use heuristics such as completely turn off derivative feedback in favor of doing nothing over doing the wrong thing. In this work, we propose impact invariant control, which essentially only turns off derivative feedback in the directions that are most sensitive to impacts, which retains maximum control authority. We show that this can be done by exploring the structure of how impact forces enter the dynamics, and that it can be applied to general tracking objectives. And we demonstrate this by showing both jumping and running. Okay, we just talked about how we confronted the challenges for control during impacts and developed a method for jumping and running. Now we're going to move on to robot manipulation and talk about work on controlling frictional contacts. I recently presented this work at RSS and it received the Outstanding Student Paper Award. When talking about robot manipulation, there are many challenges associated with frictional contact. The first is underactuation. So rigid grasps are simple for robots to think about because once a grasp is established, we can freely move around the arm without needing to think about the object. In contrast, if we don't have a rigid grasp, such as when we're dealing with frictional contact and the object is free to slide, we don't have complete control of the object, and thus we need to model or somehow account for the object state. Another challenge are known inaccuracies in rigid frictional contact. Just like how our models of rigid impact are flawed, our models for frictional contact have similar issues. Finally, frictional contact greatly complicates the planning problem. In my earlier work, we talked about how there are different dynamics per contact mode, but we only talked about contact and no contact. Well, there are different dynamics associated with sticking versus sliding as well, which introduces even more contact modes. So instead of just planning between contact and no contact for each leg or end effector, now we need to plan for sticking, no contact, and sliding in each direction. It's for these reasons that most methods treat sliding as something that should be strictly avoided. So using these waiter tasks as examples, these methods enforce a strict no sliding constraint in order to not have to reason about frictional contact. In fact, these methods don't even include the state of the object in their algorithms, meaning that in the case that the object does happen to slip, these methods have no way of recovering. Now, there are a few works that have looked into controlling frictional contact. However, the tasks where it's been demonstrated are either quasi-static or on simple planar systems with only a single contact. In contrast, the task we're going to look at in this work is a complex dynamic tray manipulation task. And in this task, the robot's commanded to retrieve the tray, then lift the tray, and then finally place the tray back at its initial position, doing so all with just its end effector. This task, compared to prior works, is 1, dynamic, 2, 3D, and 3 involves many contacts not only between the tray and the end effector, but also between the tray and the supports. This task embraces all the challenges of dynamics of sliding that we discussed earlier. The system is underactuated, and thus due to the heavy reliance on sliding, and we explore the full spectrum of contact modes, including sticking, sliding, as well as no contact. I just want to point out that it may be difficult to see, but there is actually a bar preventing the end effector from just directly grasping the object from below the center. And that's why we have to leverage sliding. Beyond just solving this task, we also want our solution to have a few following properties that are critical to achieving this goal of an ideal controller that can truly achieve general purpose robots. The first of these goals is simple target specification, which is this ability to specify targets as tasks as simple targets. So in the big picture, if we want to be able to stitch together low-level capabilities, we need to be able to specify those capabilities in an intuitive manner. The next is online generalization. So we don't require additional offline computation if you want to change tasks. There's a huge variety in terms of manipulation tasks that we want to do, and it's currently infeasible to just enumerate them all. It's for these properties that we turn to contact implicit MPC as our solution. Contact implicit MPC can plan for trajectories in real time without requiring pre-specification of the contact modes. It can support both specifying the target as simple quadratic cost and doesn't necessarily need an additional offline computation. While there are other methods such as reinforcement learning, imitation learning, a library of motion primitives, or reference trajectories that could feasibly solve this task, if we want to perform a completely different task, such as rotating the tray using a wall, these methods would require additional offline computation, such as retraining in sim, collecting new demonstrations, generating new motion primitives, or generating new reference trajectories. So if we really want a scalable solution, we really want these properties. More concretely, in terms of specifying the targets, we define the entire tray manipulation task with just 3 static targets, 1 for each of these positions, and no additional references or guides. And I want to emphasize that 3 really is sparse. Like just to retrieve the tray and place it back requires a minimum of 2. And we included lifting action just to show that we can control the tray once it's on the end effector. Okay, so how do we accomplish this? What we do is we simplify the system by abstracting away the robot by considering just its end effector. And we focus on the interactions between the end effector, the tray, and the environment. We model these interactions as forces, and we assume that the end effector can be directly controlled with inputs U. We again use a control hierarchy with a simplified model of just the end effector tray and supports is used by the MPC, and the MPC is planning for trajectories that are then tracked by actually the same operational space controller. Okay, the simplified model we use for MPC is a linear complementarity system, or LCS, and what it is a piecewise linearized model of the dynamics, and it crucially captures the interactions between the end effector, the tray, and the environment. In a bit more detail, the LCS model, we have the end effector state, which is only free to translate, so we only include the translational degrees of freedom. But the tray has its full 3D floating base degrees of freedom. So this is the orientation expressed as a quaternion, as well as the translational degrees of freedom. LCS model uses linearized dynamics, but the contact component lambda is what makes this LCS piecewise linear. We use complementarity constraints to encode the contact dynamics. In the right side is the complementarity constraint that encodes the linearized decision boundaries between the contact modes. Yeah. We're not measuring friction, we're trying to control with friction. Yeah. Yeah, so friction can also be, sliding versus sticking can also be encoded in this contact boundary. Yeah. It's
not measuring friction. It's trying to control the tray.
Yeah.
It's not like a model identification.
Yeah.
So
we're trying to move it around. We're trying to move it around. Move it around. Yeah.
Might want to show you want to just show that?
Yeah, we'll go back to the this one. Yeah, so we're trying to move the tray, but the primary method of manipulating the tray is through sliding. So we can slide the tray back on the supports, and we can also slide the tray with the end effector to reposition. That's the goal. The goal is to manipulate the tray. using a new, less used contact mode, which is sliding. So we need to think about friction, but we're just using it to control the tray. Thank you. Okay. Thank you so much. Yeah, so the LCS, okay, we have this encodes the contact dynamics, and the right side is the contact boundaries that decide between like contact, no contact, as well as sliding and sticking. So this can be encodes all of that. But yeah, we have to linearize this. This is the linearized contact boundaries. More explicitly, the contacts that we care about or explicitly capture, we use 3 to capture the surface-surface contacts between the end effector and the tray, because we're doing this in 3D, as well as 2 contacts for each support in order to capture the line contact. So this has a total of 7 total contact pairs. We don't model the interactions between the end effector and the supports because we want to avoid those. And we can automatically generate an LCS at every control iteration by leveraging Drake to for both auto differentiation as well as geometry queries to do so. And now that we've generated an LCS every control iteration, how do we plan for this? And to plan for this, we, as mentioned earlier, we leverage recent breakthroughs in context implicit MPC, which plans for the states, inputs, and forces without pre-specification of the contact modes. Specifically, we're using an algorithm developed by my lab mate Alp called consensus complementarity control, which can do this in real time. Previously, this method has only been demonstrated on a ball rolling example, which is shown at 3x. In this work, really, we're just expanding the capabilities of this algorithm by adapting it to work on dynamic manipulation and showcase that it can work on frictional contact as well. I want to emphasize that what this is doing, what contact implicit is doing, really isn't trivial. Like we're reasoning about 7 potential contacts per time step. And because we require sliding, for each contact, we have to reason about sticking, sliding in every possible direction, as well as no contact. So it's quite a jump in capabilities going from ball rolling to the trade manipulation example. How the algorithm works is it takes this LCS, constructs a typical MPC problem with LCS dynamics. We have a simple quadratic cost here and dynamic constraints shown here. The key trick in C3 is to use ADMM to decouple solving the MPC with the dynamics without the contact constraints and just satisfying the contact constraints. By doing so, we can eliminate the time coupling of the contact constraints, which is what makes it so challenging to solve. If we want to consider contact for each time step, this leads to an exponential explosion in the number of contact modes. So by basically decoupling through ADMM, this is why it can be feasible to solve. And we do this by doing multiple iterations where we solve MPC, then we project that solution with the consensus cost down to the contact constraints and iterate until we converge towards a solution that can satisfy the full dynamic constraints. To show what the MPC is actually planning for, we can draw the plan states as well as the current control inputs and the contact forces that the MPC is planning for. Show this one more time. You can also see that the current target is indeed sparse. We're just giving it a static target, and once it gets close enough, we'll give the next target. Okay, so now that we have the plans for MPC, we have to be careful on how we're tracking them because we're using forceful interactions with the object. And what we do is we adjust our formulation for OSC to be able to track feed-forward forces as well as the end effector position to stabilize around the trajectory. Yeah, the main reason why we need this feed-forward force is because the MPC is planning with contact forces in mind. So we have to account for those forces somehow, which is this feed-forward term. Okay, and just to emphasize why it's important, or like show that it is important, we do an ablation as well. On the left, we have with force tracking, which is our controller, and on the right hand side, all we do is take off the force tracking and objective, and it's slower and also just drops the tray as well. Despite like not giving it a lot of, by giving just a single target and not doing anything like fancy with the reference trajectories, the contact implicit MPC still discovers really, really interesting motions as well. So like it really heavily utilizes the supports to aid in repositioning here. And I want to emphasize that this really is indeed dynamic sliding. So in the very beginning, at the top of this, it's able to slide the tray on the end effector without even using the supports, right? It's sliding the tray forward before it even touches the supports. Our method can also handle deviations in the mass and inertia properties as well. So here we just put a mug on top of the tray. We don't tell the algorithm that there is a mug. And can still robustly handle this as well. And the mug is not light. It's about 30% of the tray mass. We do this with the sugar box as well. It's also, I want to point out that it's not just on the center of the tray, which would basically just be modifying the mass. We actually put it on the side of the tray as well. And it actually modifies inertia too. We also add in perturbation to show the real-time reactivity of the controller. And then we do run like a extensive ablation with and without force tracking to highlight its importance. This also shows just the left side is like our perfect method. It's not always successful, right? It has about 80% success rate over 10 consecutive experiments. And the main cause of failure happens when it tries to place the tray back and it slides when it's not supposed to. To demonstrate the robustness of our method, though, we perform the task multiple times without manual resets. So essentially, we're allowing the error from the previous execution to become the new initial condition of the robot. We show that we're able to perform this task 6 times before it deviates too far to execute again. Okay, so we introduced this task earlier as an example of a different task that an ideal method should be able to generalize to. To define this task more explicitly, the goal is to use frictional contact with the wall in order to rotate the tray. The tray needs to rotate again on the end effector, which means that it needs to reason about sliding contact as well. Because the tray is circular, this actually requires a lot of precision because the normal component of the contact forces, all it's doing is pushing the tray off the end effector. And really only the tangential component of friction are helpful in rotating the tray. Despite these challenges, however, our framework is able to solve this with just a single target position. Additionally, we use the exact same LCS model for the end effector and tray. This shows that our model is indeed 3D. We're able to do rotations as well. And this is really interesting to see because we don't need to find a new model for this example. I do want to acknowledge, though, that we are using different MPC gains for this new task compared to the earlier task. Okay, this is the task of robot executing the task, and you can see it's leveraging forces with the wall in order to rotate the tray. You can see the MPC reasoning as well here. Okay, in summary, we demonstrate a dynamic controlled sliding task using context implicit MPC to handle some of the key challenges associated with frictional contact. In addition to just performing the task, we identify 2 key attributes necessary for a scalable solution, which are a simple target specification and generalization to new tasks without additional offline computation. We were able to achieve the simple targets, which is 3 targets for the tray manipulation task, and then a single target for just rotating the tray. For online generalization, our method doesn't rely on any offline generated references or aids such as reference trajectories or motion primitives. And we were able to use the same LCS model across both tasks. However, we do need to tune a separate set of gains per task, so we didn't quite reach the goal of true online generalization. However, I do think this is a big step in this direction. Tune the gains for this task took less than a day. And the entire process of sitting in the office with Michael, thinking about this idea for this task, and getting to actually work on hardware took just less than a week. For future work, one of the challenges associated with frictional contact that we didn't address in this work is this very fine boundary between sticking and sliding. While we didn't evaluate this rigorously, empirically, we found a lot of sensitivity to the surface friction for the tray. While other works can get around this by incorporating some kind of margin to encode some robustness to friction, these margins are often one-sided. So basically, if you don't want to slide, you can just make a more conservative friction cone, and then you can avoid sliding. However, if you want to both stick and slide, you need kind of a dual-sided margin. And I've done some early work on this in this direction, essentially encoding the decision of which friction cone to be used as an MIQP, and we have some early preliminary results, promising early preliminary results. Additionally, we use just a single formulation for the context implicit MPC. In the last few years, a bunch of formulations for context implicit MPC have been proposed, all with slim, noticeable differences in their formulation. Beyond just, and the comparisons between all these methods have been really surface level, really just looking at like frequency and number of degrees of freedom. And that's not really, I feel like, the key differences. So it'd be really interesting to see what identify what the fundamental differences between these methods would be. And this could be really useful in informing future directions of the work and also informing which method to use. Okay, in conclusion, we started with this vision of enabling robots to perform at their full dynamic capabilities. We identified that the key challenges to achieving that goal was controlling impact forces and controlling across multiple contact modes, with frictional contact being especially challenging. We tackled these challenges head on, not shying away with the complexities of impacts and frictional contact, and we proposed methods that can overcome the challenges of each. As validation, we showcased state-of-the-art locomotion controllers, as well as a substantial increase in the capabilities of controlling frictional contact. We believe both of these directions are helpful steps towards achieving the long-term goal of developing true dynamic robots. Before I turn over to questions, I want to thank everyone that's helped me make it this far. First, so much thanks to my advisor, Michael, who taught me how to do principled research and really pushed me to understand things deeply. Michael has this incredible skill of always seeing things so clearly and explaining things so clearly. And he's been definitely the biggest influence in shaping me into the researcher that I am today. I also want to thank my committee members, Dan, Nadia, and Aaron, for their helpful advice throughout, especially on the manipulation project. Their feedback when I first proposed the project really was super helpful in choosing the direction of the in choosing the direction for that project. Yeah. I also want to acknowledge my undergrad mentors, David and Yev. David for welcoming me into his lab in Michigan, despite me not having any prior experience. And Yev for mentoring throughout, and his kindness was a huge reason in why I decided to do a PhD. Also want to shout out my lab mates, Brian and Yumain, who I worked on Cassie with. Despite not recognized as any official collaborations, getting Cassie to even function is a huge team effort. From working on the shared Dear Lab repository to our frequent whiteboard discussions, Brian and Yumain were huge help in getting Cassie to run and jump. Even like running experiments, you need at least 2 people, at least 3 people. So also want to thank Leon, Alp, and Vivit for the helpful discussions about C3 and helping with all things Franca. It's super helpful to get Franca up and running. Also want to thank Sharanya and Haoshan, who I had the pleasure of mentoring in various capacities. Sharanya is currently doing really interesting work in extending C3, and Haoshan is now a PhD student at Yale. I want to thank all of their lab. I learned so much from everyone in the lab, and I feel so lucky to be part of such a fun and supportive lab. I also want to thank all my friends throughout the PhD. The PhD can be really stressful at times, but having such a good community of friends to go through it together made it a lot of fun. And I also want to thank my family for teaching me the importance of education and being incredibly supportive of my decision to do a PhD, especially my sister Angela, who always pushed me to aim big. And finally, from the bottom of my heart, I want to thank my fiancée, Jessica. I'm so lucky to have found a partner that I can connect with in so many ways. Our backpacking, mountaineering, and cycling adventures were some of my favorite memories. I'm super lucky that she's also an incredible researcher herself, and I'm glad we were able to share the PhD journey together. Okay, with that, finally, I'll open it up to questions.
We'll start with some questions from the committee. Dan, do you want to start? Oh, Aaron, let's do Aaron first. Yeah.
I can't really hear anyone other than Will.
Yes, I can hear you now. Yep.
I can't hear anyone else, just so if someone says something, you got to repeat it.
Okay. Sounds good.
I'm guessing you want me to ask questions now.
Oh, yeah, that is what Dan said. Yeah.
Okay, great. All right, awesome talk, really cool stuff. Yeah, I had a couple questions. I think thinking back to the first half, the sort of impact and variant stuff. Um, when you show that you say that the impact takes this amount of time, and is that really that the impact takes that much time, or that once you have an impact, it takes time to sort of propagate up to these other joints in the robot?
I think it's both, but I think the compliance in the joints can definitely add to when different joints feel the impact, but also just if you have like like even just like a solid rigid object and it touches the ground, that impact doesn't resolve instantaneously, and even like a very rigid object could still take on the order of like 10 milliseconds to resolve. So
Yeah, I mean,
uh,
no, but 10's a lot less than the 60 you were talking about, right?
yeah, yeah. But I think especially when we move to more like human scale robots where there is like a lot of mechanical compliance, I think it is still like a significant delay or a significant duration.
But if it's sort of compliance in the joints, couldn't we still treat it as a fast impact and then have a compliant model of the robot to see how that propagates?
Sure, but I think making a compliant model of the robot when it's near rigid is, I think, more complicated than I guess you could, but I think trying to model near compliance is really challenging in its own right.
All right, and then the key idea is you take this projection, and then I wrote down slide 21 if you want to go there.
Yeah.
But you sort of had a plot of the velocities after the projection, before the projection and after the projection, and you get rid of all the discontinuities. Yeah, here on the right, you label them as pelvis X, pelvis Z, left hip, left knee, all of this. Are those really, should we interpret those as those joints, or have we projected to some kind of other space that isn't exactly these individual joints?
Yeah, I think they're not quite these joints. I wanted to, in some of them, it is almost, if you look at actually the left knee, the purple line, you can see that it's actually very similar, both pre and post projection. Uh,
Mhm.
and that's because it's like the farthest link away from experiencing impacts. So in a way, it's for some joints, yes, I would say it's not the same thing at all. But if it's like if it really isn't experiencing impacts, it's not going to modify and project it to some really weird space if it doesn't need to.
Yeah, so I mean, I would just caution against, calling it. I mean, all right, so that's the one that looks the most like. But then if you look at right knee, the
Yeah,
light
it's just
pink
zero.
one, it looks nothing like the other one, including before the actual sort of impact time.
Yep.
Um,
Yeah.
and so then I just want to be a little careful that we don't want to think about like, oh, if you look at the right and you're like, oh, the right knee's not moving at all, when actually it's like moving really quickly.
Yep. Yeah, I
Uh,
agree. I think that's yeah, I think that's a very good point.
All right, and then on the second half, you said, oh, this uses some kind of contact implicit NPC. Can you just sort of briefly explain how that works?
Yeah, okay, so we have our LCS dynamics, and we can MPC what it's doing is just saying minimize some quadratic costs over some time horizon subject to the dynamics. The orange thing or yellow on the projector, this is just the expanded version of the complementarity constraints, right? We have each side of the complementarity constraints plus the bilinear term.
Mm-hmm.
So this is the most general like MPC problem for LCS dynamics. And how the algorithm works, this is not, I want to be again clear, this is not my algorithm. This is my Leibniz Alps. What it does is use ADMM, which is we separate the problem into two, and then we essentially alternate between the two with some consensus cost to make them essentially match. But more explicitly, what we do is first we solve MPC with just the part in pink. And what this does is essentially we can pick any lambda. There's no constraints on lambda anymore, so it's free to pick any contact force. Essentially, the contact force that helps it achieve its goal. And we take the solution with some costs, essentially try to match the solution as best you can, but project it down to the contact constraints. Now you have to satisfy the contact constraints, but you want to match the MPC's solution as well. So now, okay, if you thought you can get a contact force lambda, but you're actually far away from contact, that lambda might get projected to 0. And now we're going to go back to solving MPC, but now with, again, a consensus cost to match those now projected variables. And now MPC knows that, okay, maybe I wanted to get a contact force lambda, but now I can't. The projection tells me I can't. And then you're hoping that through this consensus cost and through iteration, that these two solutions that you get from each of them separately converge together to give you a dynamically feasible solution. In the key,
Yeah. Okay. Yeah. I mean, I guess the part I'm and this, as you say, it sort of wasn't your development. I just want to make sure I understand how the rest of this is then using it. So then, when you go back to the solving the MPC without a contact constraint, wouldn't it just put that force back in if it wanted it?
yes, but there's a consensus cost for both. It's not just sorry. Yeah. Oh. Yeah, so in addition to so it's not quite exactly solving this and then projecting this, there's also a cost objective that says the solution from, so this will give you xu lambda. It's slightly different because we're going to do this per time step, the projection per time step, but there's also a quadratic cost says the xu lambda that you're finding from projection there is some cost to the difference between the solution from the MPC.
All right, so there's an extra term that's not shown on this slide.
Yes, the consensus cost is not shown on this slide.
All right. And then in terms of this
So Dan, was that clear
step, especially with sort of frictional sliding, there's like infinitely many ways you could project it onto a feasible contact dynamics.
Yeah.
Is there any trickiness with how you do that projection?
Yes, infinite wave projection, and there's also there's a choice in how you actually construct the LCS. Like, how do we turn this? Like, how do we find the lambda, and how do we actually get these contact boundaries? Right, there's a lot of ways to write a discrete time-stepping contact model. Yes, there is a choice in all of this. For this work specifically, we use an Aniszewski model, which linearizes the friction cone to just 4 directions. That's how you get around the infinite ways to slide, directions to slide. And although it can support more, 4 seem to be enough. And then what's the next question? Oh, how do you project it? Yeah, so there's also a lot of ways to project it. What we do is we solve the LCS explicitly. We use the MIQP, essentially picking which bilinear term to be 0. And we solve an MIQP where the binary decision variables are which one should be 0 to encode each decision boundary.
Okay, so you have like an integer variable for sliding versus sticking kind of.
Yeah, sliding versus sticking, contact, no contact. Yeah.
All right, and then you're solving this in like a collocation kind of framework.
No, we're not doing. It's just there's no fancy integration for the dynamics. But if you mean just like a time stepping, like a time step, like a trajectory optimization problem with knot points, yes. But I think by collocation, not like the fancy collocation constraint.
That's fine. First order is it's just collocation. Okay. All right, and then looking at the results there, I was looking at especially the one with the mug or the one of these. So it kind of does this pawing motion where it tries a couple times and goes back.
Yeah.
Is that an emergent property? This sort of try again?
Yeah. Yeah. So the number of times is no predefined number of times it's trying to like pull it on. It just keeps trying. I mean, this all comes out of context implicit MPC. I'm not like pre-specifying anything about this. So this is just purely emergent behavior. So if you look at this is a good example. Like the sugar box it has a different number of attempts as well. And if you look at actually the like 6 consecutive experiments, there's actually a lot of different strategies, or it's mostly still like pawing it, but like there's a lot of diversity in terms of like how many times it takes and how far it goes. So if you look at this one, like sometimes it does it really quickly, just a few times, and sometimes it takes a few more times than to actually be successful.
So if you're gonna have to go, paw at it multiple times, if it had just gone, lifted straight up, and moved a little slower backwards, wouldn't it have worked the first time?
Yeah, so you can imagine that like if you're very careful, you can try to do this quasi-statically, except for you might have issues right when it like transfers from the supports being completely supported by supports to just on an end effector. You could do that. What we want to do is like really leverage sliding, is to kind of force it to do it more dynamically. So this type of behavior of like going faster but maybe missing a few times was something that we actually optimized for when choosing the gains. And to be
I'm just
fair,
thinking that if it's gonna take a few attempts, the quasi-static thing might be faster.
yeah, I would agree. I think the main limitation actually comes from the frequency of getting the trace state. We use an off-the-shelf April tag. We use an off-the-shelf April tag that's really slow at 10 hertz. We thought it might not work, but we tried it and it seemed to work. But if you give it like full, like super high frequency, let me see if I can find it. If you give it high frequency in true ground truth state, it does it much faster. So it's not like I think yes, in practice, maybe it's slower than doing it quasi-statically, but it doesn't have to be.
And is this one, is it still faster with an unknown weight on top?
I didn't test that. I don't know about that one. And this is sim data. This is not.
Yeah. But you could test that in sim pretty easily. Because I assume that the polling had to do with the sort of model mismatch, that it came up with a plan and then the thing was heavier than it thought, so it didn't get as far, and so it had to go again.
Yep.
Can you guys explain what you mean by quasi?
All right. I'll stop here and pass it on to the next committee member.
kind
And
of do
just, repeat the question so that I can hear the
Yeah.
question.
Yeah, I will.
I'm not convinced you can do this quasi static.
Michael says he's not convinced you can do this quasi-statically. I think you could. I think you could. It depends. Yeah. Depends on like the gap, the lip of the table. Yeah. 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 Yep, exactly. Yeah, you can. Hmm. Oh, interesting. Hmm. Yeah. Yeah, definitely check it out. Super cool.
I want to start by congratulating you. It's really important. Try to think. So flights. I'm uncustomarily complimenting. Okay, so congratulations for this. I think it's very landmark work. I'm confused about a number of things that maybe I'll take offline. Before you escape. But I think demonstrated massive robustness against massive, benevolent groups. I'm confused that you were able to get. Let me before I go to confusion. Your feeling is that you're somewhat sensitive to the stick slip. But I would have thought you would say that you're very to this feet into the parameters of the stick slip. And I would think you'd have to.
Yeah.
But I'm also suspicious that you've chosen your the model that you use to choose the contact points in your model must be very sensitive as well.
Mm.
They have to be very sensitive as well. And I wonder how magic it was for you, like the contact points to get a model that would actually do present things, or whether it's just, don't worry, Dan, you do it in your sleep.
No, all right, so Aaron, Dan is asking about the sensitivity to the chosen points of contact. Like when we actually make our else. I'm really surprised that it worked for this task because we have to do like we're rotating the tray on the end effector, which the fact that you can capture that like rotation friction. Yeah. I don't think yeah. I wouldn't say it's perfect, right? I think we're not. If it was completely perfect, you would imagine to be this. Yeah. I would say there's actually there's actually no magic. I think we do need minimum 3 because otherwise we don't essentially adjust the contact points. So if you had less than 3, you can, if you try to pick it up, it just fall off. I think we chose the minimum is basically the choice. We chose, you need a minimum of 3. We chose, because each contact you're adding really complicates the number of like decisions you have to make. We really chose, I guess you can get rid of one of these supports and make it for 6. So, yeah. Yeah. Yeah, I mean, luckily it worked out. I think this was an intuitive way, and I think it's very nice that we were able to get it to just use an intuitive like choice of contacts, because that means like it can be used for other tasks as well. But no, there wasn't anything special or like any. Yeah, thanks so much for coming. There wasn't any like very special like choice behind the contact points that we chose. We wanted to make it symmetric. We wanted to use like the minimum at least the minimum number, but beyond that, we didn't really pick anything.
Shouldn't it be as at least as susceptible to the choice of contact? Both should be.
I'll say that it's very sensitive to the height. Like we're using a fixed model, and if you get the height of the supports wrong, yes, you're gonna. I mean, if you think the tray's like higher than it, like lower than you think it is, you're just gonna whiff every single time. You're not gonna be able to recover. Actually this one kind of matters, the one in the back, because you want it to be able to support the tray at all times, but I don't think it didn't matter too much, is I'll say. Yeah.
The piece of that is very in what Aaron is getting at, just the perturbations, the real-time perturbations demonstrate that you're letting in see in real time.
Yes.
Otherwise, you could never patients.
Yeah.
Everything, every little, I don't know very much about it. My students.
Mm-hmm.
There's some, I can't understand how the horizon, if the horizon, if your end, if your horizon event is super short, I can imagine that the other way work. Your horizon presumably has to be very, very long because you're giving very, very parsimonious task information. How are you able to do this computation in real time?
Yeah, so it's not, the horizon is not that. So Aaron, Dan's asking about how is MPC even able to reason about these types of motions so quickly? Sure. To converge to these motions in this time, especially given like the horizon of this task, we're given very sparse targets. How is it even able to do this? I think it depends on the task as well. I think we're giving like one sparse target, but I think it doesn't necessarily have to reach the target and know the exact motions of reaching the target. It just has to get closer. And I think that's comes in somewhat into play that the horizon actually isn't that long. It's like half a second. Yeah, sure. Yeah, but we're doing n is 5, which n is 5. Yeah. Yeah.
Why should you expect that you're naive consensus? What I understood you to say is that all you're doing is you're tossing both of them, you're tossing them this.
Yeah. Yep.
But you're penalizing the previous. There's no way that NBC is going to tell it.
Sorry, I'm a big. There is like theory on ADMM guaranteeing to converge if you give enough iterations. We don't actually solve to convergence, but there is some theory about like ADMM these will agree at some point if you run enough iterations. So what was the other part of the question? Oh, this is only a single iteration. This is a single MPC solve. The 30-60 hertz includes all these iterations. Like this one solve includes, I think we use 2 or 3 iterations, and that's all included in one solve. So there isn't like a mismatch in terms of the state. Like this actual state of the system is consistent for these iterations.
Right here that you don't converge.
Yeah, I think it's, yeah, sure. We don't converge. We solve a fixed number of iterations to get the speeds we want, and we're basically hoping it's kind of the magic of like Boston dynamics, where like you trying to get close, and hopefully for real-time control by solving it fast enough, you get close enough towards the solution that it doesn't matter. Oh yeah, so I mean, it does fail, right? It does fail. Like we don't say it's 100% success rate, right? It definitely does fail, and I think we don't want to hide that part, right? We're trying to solve a nonlinear. Yeah. Oh, I mean, you can get like that's the reason why we had 2 different set of gains is because we're really just choosing a specific local minimum. Oh, to get it to fail. I mean, in practice, it's very sensitive to the exact. Even for this experiment, it takes a very specific set of gains to get this behavior because we're really just choosing one local minimum from this nonlinear problem we're trying to solve. So, like the gains I picked are something that makes it dynamic, and the rest of it has to make sure it even converges to like a reasonable solution. Like, it's a bunch of gains. Like you can't. Yeah. Yeah. Thanks.
Well, I have some follow-up questions on what you were asking. So
Yeah.
also in regards to the physical perturbation part. So like if you show the videos at the end, I was also surprised how like the MPC was able to handle them, and it doesn't seem like it's recovering because I actually thought that you were pushing the robot. All you're doing is pushing the tray.
Yeah.
Right. So all you're doing is like you're physically perturbing the state of the tray. And you're limited basically by the perception system, right? Like, so you would react to that change in the, so your April tag, you said it was 10 hertz?
Yeah.
Or like, so you're updating the state of the tray at 10 hertz, your NPC is running at 30, 60 hertz. So your controller is actually running faster than the perception. So that's why you are capable of, I guess, being reactive to that perturbation. But if the perturbation would be on the body of the robot physically, would you be able to recover from that?
So I want to clarify the inputs to NPC are not just the state of the tray, but also the state of the robot. So that's why, like, if it was only the state of the tray, then we really don't even need faster than 10 hertz. There's no point because we wouldn't get our measurements kind of stale anyway. But I think if you were to perturb the end effector, it'd actually be easier, right? Because we have state feedback at a kilohertz, and we're directly controlling the end effector. We can just react. I think perturbations on the tray are actually much harder because of the delay, but also you can't directly control the state of the tray with your motors. You have to like do it through friction.
So the other thing that I was wondering is you mentioned that, so in some of the experiments that you showed where you're manipulating like the mug and the sugar box, you're not really modeling those objects at all, right? Like you're kind of like assuming that they're just perturbation.
Yeah.
There's kind of like a perturbation on the model of the tray that you have. But what if you did want to, like, what if the mug had coffee in it, right? Like, what if it was like glasses of, champagne glasses or something like that, where you did have to be a little bit more careful in these like dynamic sliding motions. Could you introduce that into this modeling framework of maybe like some simplified model of the object that's also in contact with the tray?
Okay. The question from Aaron is from Nadia is basically we don't model the objects on the tray, but could you do something? Say you want to be more careful, like the mug's like moving on the tray. We're not really carefully controlling the position of the rug. Is there a way in our control framework to account for this? One video actually I probably should have put it in this talk was that we do, but one additional thing to show that we can update the model is we just stack two trays on top of each other. Well, it's just so like, we have an April tag, it's not including the April tags, and we update the model in our system to include the additional thickness, the doubling in the weight, as well as the change in inertia, and we can actually handle it really well. Actually, when you have two trays, it actually doesn't work anymore because it's too much of a disturbance. But if you update the model, it works. That's if the objects don't move relative to each other. If you want to control the mug on the tray through the end effector, that was something that we were actually talking about. I tried to get it working in simulation. It was really hard. Yeah. There is if you tune the friction coefficients, there is a region where you theoretically should be able to control both simultaneously, but in practice, that was, yeah. I mean, if you try to get a human to do it, that'd be like really hard. Yeah. But theoretically, it could work, and theoretically the framework should support it, but I think in practice, it'd be very hard to achieve.
So, and I had some questions about the first part as well. So if you go to slide 19, so, well, I mean, first, for my questions, I also want to say what Dan said. This is very impressive work. The fact that you got that you're solving these contact problems both on locomotion and manipulation is very impressive. And the videos of the sliding are amazing. And there's no wonder you won the outstanding student paper award at RSS. So I just want to congratulate you for your next work.
Thank you.
But I was just wondering about just this slide, for example. If you plotted this trajectory on the phase space, like velocity versus the position of contact, you no longer have this kind of hybrid, trajectory, right? You would have something like a curve that maybe makes contact, and then you would end up with some chattering or something like this, and then you could control for this.
Isn't there still a reset map even in phase space? I'm pretty sure there's still this continuity in phase space.
There could be a smooth, yes, yeah.
Yeah. Oh yeah.
So So what I'm getting at is that this problem is obviously super difficult because you want to be able to like control for that time, the timing of contact pre and post contact. But could there be a way to like alleviate that by thinking about this other, like in the face space, right? Like you need to do this because you're tracking a time reference trajectory.
Yep.
But what if you're not tracking a time? Like could you track something else like a phase space trajectory that's more state dependent? And then this problem would be less finicky or less difficult to really that you really need to kind of like control for those timings, right?
Yep.
Because, and you kind of mentioned this, like imagine that you have, you know, an actuator that has some mechanical compliance, then maybe you don't need to be like that precise, like because the mechanical compliance like will be kind of like absorbing knots, right? So this seems to be applicable only to robots that are kind of like very stiff or that don't have like such mechanical compliance or a capability of absorbing the impacts, such that your control is kind of like simpler. So I was just wondering, like, would you still need something like this if you had a robot that had better capabilities in terms of like being more compliant with the environment, being able to be more, you know, be capable of that the actuators actually absorb like these impacts?
Right. Aaron, I think there's now yet two questions. One was if you got rid of the timing, essentially did like phase space, like only the reference is not defined with respect to time, but defined with respect to your state, could you kind of avoid this timing uncertainty? There's actually interesting work, kind of similar, the same lab as this one, essentially doing that. But I think the challenge for stiff systems is you're still relying on velocity measurements to know where you are in phase space. And we just can't trust our velocity measurements during impact because like if we're changing quickly, but to actually estimate velocity, we had to find different encoder readings, and to get rid of the noise, we had to add in some filter. And like at the time scales that impacts for stiff systems that impacts resolve, the filter dynamics actually do matter. And you can't really basically you can't trust your velocities to actually be correct. There's like delays from introducing the filter. So I think that's the one challenge of doing that. But that's only valid for very stiff systems where those impact dynamics are like that. There has been there's a lot of interesting work actually like a while ago on like more like compliant actuators, right? Like series elastic actuators. They kind of like dampen the impacts. Cassie actually has some of those springs. In practice, I think the field has actually moved away from actual mechanical compliance just because they're so hard to control. These add additional degrees of freedom you can't actually control. Like if you look at like in favor of more direct drive actuators where they do actually experience impacts really quickly and kind of fake your compliance in a way. So I think yes, you could dampen out the impacts a bit, but I don't know if that's the direction that the field's going in terms of mechanical design. Maybe we'll go back to it. Maybe we'll add in more. We'll realize this is too much of a problem that we should have some more like real mechanical compliance in our actuators. But I think currently, if you look at like the quadrupeds, and even if you look at the new like iteration of Cassie, they actually get rid of the springs because they actually turn into like they're. I wonder if so these leaf springs, which are this black thing, they actually replace it with just like solid aluminum for a digit, which is like the new iteration of this robot, because it's like talking with everyone who works on Cassie, these are like a huge pain point in terms of control because they're like real mechanical compliance with they're stiff, but they're not quite stiff enough that you can just treat them as rigid. But
is this something, is this a trend just for like Legged robots? Because for manipulators, everything at like almost all the collaborative robots are series elastic actuators or some form of like they have to have some drivability. And also the torso of the humanoids that also have like these type of motors, right?
I think I would say this work is really aimed at where the impacts do happen really fast, but not instantaneously. I think if we can model the compliance and it's feasible to measure them, I think we can look at other methods. This is like kind of the most extreme example where we say we don't know what's going on, so we're basically essentially giving up entirely. I think if we have better models and have better measurements, I think we can definitely do better.
Yeah, I see that the difficulty in getting like the good measurements, yeah.
Yeah.
So there's another slide that you said. So when you're activating the slide 24, activating the projections based on this high level plan that you get, right?
Yeah.
And there's something you mentioned at the beginning that you don't have any restrictions on how fast the high level, so you're not replanning at all the high level plan, which is like the trajectory that you want the robot to follow.
Yep.
But what if there are some unmodeled things in the environment, right? Like right now, the experiments that you're showing are just Cassie running on a flat terrain. But what if there are like rocks that you didn't see before, or that maybe there's like perception failure that you don't see that? So would this framework be, because it seems like it's impact invariant if you are expecting the contact. But if you're not expecting it, and if there's like some disturbances, and you show very nice kind of like time perturbation where you're saying, okay, maybe we make contact before or after, but the point of contact is the same.
Mhm.
But what if that changes? Like, can that be like, is this method robust enough to also kind of like, let's say, state or environmental perturbation?
Okay, so again, two questions. First is just clarifying that we do need to know the expected timing. So if we were to like say like hit a rock that we never knew was there, could this be robust to it? And the answer is no. Right, we do need to know the anticipated, not only the contact like timing, but also where, right? If like we were to like hit the knee on something, we're not doing anything about that, right? We need to contact Jacobian still. So the answer to that is no. And then the other question is, can it handle, we just did time disturbances. Can it handle state disturbances like geometry disturbances as well? Actually, in the early conference paper, that's the disturbance I looked at, which is just jumping onto different platform heights, like very small perturbations, but like up and down. And that's another way to change impact timing as well. Yeah, so it reasonably handled those, but yeah, if the contact Jacobian is really wrong, right? That's something we're not accounting for, differences in contact Jacobians. Then if it's like really wrong, it's like a weird angle, then I don't think it would do as well.
Like if you had a way to like very robustly estimate all the contacts, suddenly it really goes and it pushes you, and then you can estimate the contact.
Yeah.
The contact Jacobian, you would be able to include it into this framework. Right?
Yeah, so we couldn't include any contact Jacobian, any timing into this framework, but I think in practice, we don't, like, you'd almost be like super conservative if you always had to, if you knew about it, you can do it, but you kind of operate on the assumption that you don't know about it. So if you're trying to say like, oh, I can get contacted from anywhere, then you'd be like super conservative. And I think this is definitely not the framework that you want to use. Yeah.
Any questions from the audience?
Yeah, Ethan.
So you did not use here OSC the projection of the impact variance space for calculation, right? Is there a particular reason where the impact force is small enough, or sort of necessary?
Yeah, so we could have, we didn't, just because it ended up not being necessary. I think the discontinuity that we're scared of in jumping is coming from much larger impact forces than we are from touching a tray. But you could use this. And actually, the very, very initial inspiration for this task was trying to combine impact invariant for like picking up a heavy object really quickly. So that actually was part of the consideration, but in practice, it wasn't necessary, so we didn't do it. Almost, I think if you can measure the velocity accurately and define the actual path that you expect the impact to take. Maybe like if you have perfect sensors, you can like just use a data-driven model and like create a model for impact that actually happens. Yes, you could do it. I think I mean, yeah, I think you had a infinitely fast sensor, and you knew what, and you knew exactly the path from pre to post impact velocities. I don't think if you like basically like made this like long enough. Yeah, yeah, yeah. I think if you basically expanded impact to be like so they're not so fast, and you can treat them as not fast, I think you could totally do this. But I think in practice that's very hard to. At some point, you're gonna like hit like some physical limit of what we can do with actuators and sensors. Yeah. Yeah, yeah, one of the comments I got during RSS was, can you make a quadruped like skate on ice, like Bambi? Well, not as uncoordinated as Bambi, but like yeah, essentially do that. I think that'd be a really fun project. I think like work like locomotion on very like slippery terrain, I think is underexplored. And there's some like reinforcement learning methods that try to handle it, but I think explicitly trying to like control for sliding for locomotion would be really interesting. I think theoretically it could handle it.
Any other questions?
Ask everyone else.
Yeah, okay, let's give part of it is maybe to the room. You know, look at it.